Hi there, I'm Phil Atkin. I'm the guy writing PIANA, the Raspberry Pi synthesizer. So last Monday, went to the second Bristol Raspberry Jam event, showed the synthesizer, attempted to show a slide deck, but we had all sorts of IT multimedia problems. So decided to commit the deck as a video to YouTube so that everybody that saw the disaster on Monday can see it done a little better today. And people who couldn't make it Monday can see it anyway. So let's start. So we'll be talking about synthesizers, a bit about synthesizer terminology, some synthesizer history, talk about the development timeline of PIANA, talk about phase distortion, which is one of the key synthesis techniques used inside PIANA. Go into a bit of gory detail about the software, which you probably don't care about, but I'll do it anyway. Talk about the prototype hardware, and then give you a swift demo of PIANA as she sits right now. And then we can talk what's going to be happening in the future. I may switch the order of that. Actually may do the roadmap before the demo, but we'll see. So here's a definition of a synthesizer that I found somewhere near Wikipedia, which probably means it's full of nonsense, but who cares about that? It's accurate enough for me. So an electronic instrument normally played by a keyboard, producing a wide variety of sounds by generating and combining signals of different frequencies, here's a few synthesizers. So classic analog one bottom left, classic digital one top right, classic millennial synthesizer, which is your iPad bottom right, and top left is my Raspberry Pi synthesizer that you'll be seeing later. So here's my potted history of synthesizers through the ages. Really critical one, 1928, really the first synthesizer that you would recognize as a synthesizer. This is the Onde Martenot, invented by a French geezer called, I think, Maurice Martenot, if memory serves. Real synth, made some pretty brilliant ethereal Bela Lugosi kind of sounds, played by a keyboard, really looks like a synthesizer. Next one I shall call out is the Chamberlin and Mellotron from the 50s and 60s. Now, the audience at Bristol were sufficiently switched on to really give me a hard time about skipping over the Hammond Nova chord. And I have to, hands up, I should really have included the Hammond Nova chord in this list because it's a cracking synthesizer, absolutely vast, literally the size of two separate gorillas. And it had envelope generators, had subtractive filtering, it's kind of great. But I just chose to skip over that one and go to the 50s, 60s tape-based sampling with the Chamberlin and Mellotron. 1970s then, the Mini Moog really brought in synthesizers as we know and love them, with modulated oscillators giving harmonically rich signals, envelope generators shaping those signals and shaping what the filter does at the back end. And a filter to selectively remove and amplify frequencies, and it's that selective removal of frequencies that gives the name subtractive synthesis. Hit the 1980s and everything went digital, and pop music would never sound the same again, and in fact would sound pretty dreadful from this point onwards, and I entirely blame digital synthesizers. The DX7 introduced in 83, an FM synth, depending on who you speak to actually, either a frequency modulation or a phase modulation synth. Calling out the Casio CZ1 because phase distortion is a key part of what PIANA does, so I regard that as an important device regarding this particular presentation. And then with sampling going digital, emulators, synclaviers, Fairlights, suddenly you had the opportunity for awful hit records featuring nothing but sampled dogs barking. So there you go, the 1980s, everything went horribly wrong. But that didn't stop me wanting to build a really retro 80s synth. So the timeline of synthesizer history, as you've seen, goes back to the 1920s. The timeline of PIANA only goes back to May 2012. Now, for people who are watching this in the future on YouTube, the present is October 2012. So, round about May, I actually had a rather strange dream involving a synthesis technique and thought, oh, I need to write an oscillator that does that. That would be great. And I really thought I'd invented a completely new-fangled synthesis technique. It transpired when I started researching it that Casio had done this 30 years previously. So there you go, there's nothing new in this world. I was originally targeting, before the Raspberry Pi came along, was targeting a dual-core 1 GHz ARM Cortex A9 a much, much faster and more powerful chip than the Broadcom device and the Raspberry Pi, which gave me all sorts of problems when I started to optimize for Raspberry Pi later. So the original concept behind the synth was it would be a pure phase distortion synth. We even had a manifesto here: there shall be no filters. Which is all well and good, having a manifesto, but if it sounds horrible, you better rip up your manifesto. And it didn't sound good. The first version of the modulated oscillator that I put together in this May-June time frame sounded pretty dreadful. So rewrote it, added filters, actually rewrote a lot more than just adding filters, rewrote the aliasing management code, and had me an oscillator that modulated and sounded pretty sweet by the June-July time frame. My wife gave it a name, which was PIANA, the polyphonic virtual analog synthesizer. Now, by which time, I'm being a bit revisionist here, my Raspberry Pi didn't arrive in the post in July. It actually arrived in the post in May, and I did nothing whatsoever with it for several months. And then remembered, in about August, I got this Raspberry Pi and thought, you know what, maybe this synth can be crammed into this tiny little processor. Let's see what we can do. And hey presto, PIANA, the Raspberry Pi port of PIANA, was born. So PIANA does the following three things to synthesize sounds. It's a virtual analog synthesizer, so it uses digital representations of oscillators, digital representations of envelope generators and filters. So it's a classic mini-Moog style subtractive synthesizer, but it's fully virtual, as you would expect. It's a digital analog of an analog synthesizer. Uses phase distortion in order to get its underlying oscillators to sound harmonically more rich, so you get a lot of complex harmonics going on as a result of the phase distortion, which just sounds great. That's the whole point, is to make it sound great. And also, coming very soon, sample-based playback, so Mellotron, Fairlight style stuff. Phase distortion. I'm going on about phase distortion a lot. What is it all about? So here is a sine wave for you all. Now, when we apply phase distortion to this sine wave, the period of the wave isn't altered, so it kind of end to end, it lasts the same amount of time. But what we do is squash the notion of time early in the wave and stretch time late in the wave. So watch this transition. You can see us phase distorting. So bottom left is effectively linear phase, undistorted time. Bottom middle shows you how phase, i.e. time, is being distorted over the lifetime of a single cycle of the sine wave. And you can see the result on the sine wave here. So the early half of the wave gets really squished, the late half of the wave gets really stretched. What that does, the fundamental, so the note that you perceive, so if I'm playing a C on a keyboard, if we apply this phase distortion, it's pretty obviously still a C. But lots of harmonic richness comes in, so the note sounds way more interesting than it would were it not phase distorted. And as you know, as you all know, of course, a pure sine wave has no harmonic content whatsoever. So we're actually adding harmonic content where it didn't exist if we're applying phase distortion to a sine wave. Here's a quick burst of phase distortion for you all. So here's a square wave rather than a sine wave. It's currently not phase distorted. And as we start to bring the phase distortion in, you hear it sounds really groovy and digital synthesizer-y and kind of great, really wild, General. So there you go. That's the underlying modulation technique that we'll be using a lot of to make the synth sound cool. Internally, the software looks like this. It's heavily multi-threaded, as you might expect. It's a really hard real-time system. Lots of stuff has to happen to schedule. You can't have a high degree of latency if you're trying to play the piano. The notes can't come out half a second late, so you can't be late sampling the keyboard in terms of when it was hit, and you can't be late presenting sounds to the loudspeaker in terms of when they're supposed to come out. So lots of threads, some of them prioritized high, some of them prioritized less high. There's a thread reading the keyboard, the MIDI input thread. the brains of the whole thing is the human-machine interface thread. That's the central command and control. It really is the thing that makes PIANA behave like PIANA. There's a collection then of synthesizer engines. So there's a phase-distorting virtual analog synthesizer engine and a collection of sample-based playback synthesizer engines, which are in the process of being developed and turned on. The HMI human-machine interface communicates with the synthesizer engine to tell it which notes to play and how to play them. It also communicates with the OpenGLES presentation layer to tell it what to draw, i.e. what you see on screen is being controlled also by the HMI. The synthesizer also has to talk to the OpenGLES presentation layer in order to do that fantastic green oscilloscope thing. So HMI is talking to the synth and is talking to the OpenGLES layer, and the synth is also talking to the OpenGLES layer. The synth then, having synthesized its bytes of data, pushes them out to the loudspeaker via a native audio thread, which on the Pi uses ALSA. On the Mac and under iOS that uses Core Audio, as you would expect. And then the audio goes out to a Marshall amp, and the video, the rendered pixels, go out to a telly. And there's the thread structure of PIANA in a nutshell. A bit more detail on the virtual analog synthesizer thread, which is where all the really heavy-duty synthesis happens. I'm just going to flick through all this and get all the information on screen. So bear with me as I hit the forward button. So there we go. So MIDI commands routed into the synth via the HMI are used to trigger the oscillators, to tell the oscillators to play a C or a C sharp or whatever. MIDI commands are also routed through into the modulation matrix, which drives the phase distortion parameters into the oscillators, and does all sorts of other stuff as well. So the audio flow is in red. The oscillators generate audio signals which go out to the filter. It's then low-pass filtered, resonant low-pass filtered, out to the native audio thread. Lots and lots of gubbins happening inside the modulation matrix. So for example, on your classic MIDI keyboard you have maybe 8 or 9 sliders, rotaries. Those sliders and rotaries come in via the HMI layer into the modulation matrix, and then in conjunction with the 4 envelope generators and the 2 low-frequency oscillators do all sorts of munging to what the oscillators are doing and what the filter is generating. So lots and lots of stuff happening inside the modulation matrix, driven by the instantaneous values of the envelope generators, the low-frequency oscillators, driven by instantaneous readings of MIDI continuous controllers, and also MIDI keys, because the filter in classic Moog style is resonant and tuned, so you can in fact play the filter as an oscillator. In order to do that, the modulation matrix and the filter need to know what key you're currently pressing, so keys as well go into the modulation matrix, not just continuous controllers. Breathing in. So the modulation matrix, as originally formulated, was insane and remains insanely complex. So any modulation output can be driven by any or all modulation inputs. And the outputs, for example, phase distortion amount, resonant frequency, volume of the noise generator. Example inputs are various continuous controller inputs, the key velocity, outputs from the low frequency oscillators and the EGs. Literally anything can happen, which makes the thing virtually impossible to program. Even for me, and I'm dead clever, right? So, I've simplified the modulation matrix enormously, effectively griditizing the modulation space. So there's a set of templates, VCA template up at the top, phase template, pitch template, filter template. If you look at those, it's pretty obvious that there's simply a 4-bit control going into each of those. So I've got 1, 2, 3, 4, 5, 6, 7 4-bit controls going into the mod matrix. So selecting up to 2 to the 28, I suppose that is. Combinations. Still a brain-meltingly high number of combinations, but nothing like as brain-meltingly complex as the original formulation, which I did at one point work out would take around 10 times the lifetime of the universe to audition all the sounds that PIANA was capable of generating. And none of us have got 10 times the lifetime of the universe on our hands. So, that was the software. Hardware. how do you connect a keyboard to a Raspberry Pi in order to turn it into a synthesizer? The simple answer to that is MIDI. MIDI is dead easy. It's serial. It's actually current loop rather than voltage controlled, so you need to remember Ohm's law and Kirchhoff's law, and you need an optocoupler. But apart from those minor considerations, brainlessly easy to build your own MIDI interface. And I'm the most ham-fisted hardware guy you ever met, right? And here's a couple of MIDI interfaces I built. This one's built out of a tin of mint with 3 gorgeous LEDs in it. And here's one I built out of a piece of plywood. Now, I did actually decide that MIDI interfaces in tins of mints and on pieces of plywood were not the best way to give a demo. So before I brought my Raspberry Pi to the Bristol Raspberry Jam last week, I decided to build something that looked a bit sleeker than that. So I built me an integrated unit which had a little telly. So I found a teeny tiny TV, 15 quid on eBay. You can't say no to something that's only 15 quid on eBay, right? Had to modify it to bypass the internal 12-volt regulator, so it was driven by 5 volts and hence could be driven purely by USB. And I looked up how to do that from somebody else's blog, because why invent the wheel when you can cheat? So thanks to SK Pang there. USB audio interface. The analog audio output on the Raspberry Pi is absolutely horrible. It's only 12 effective bits, pulse width modulated. There isn't a real DAC, so you don't want to be using that. The only other audio output device on the unit is via the HDMI, so you don't really want to have an HDMI TV with you if you're trying to play a synth on stage. So for £1.50 on eBay, USB audio interface, and we can rock. Matrix board, just over £1. Nice box to put it all in. Was free because an ADSL router at home broke a couple of years ago and I retained the box for various reasons. Lash it all together using a soldering iron, and there's an integrated synthesizer, and it's dead cute, and you'll see it in a little while when I show you the demo. But we don't want the demo just yet, do we? Let's talk about the roadmap, do the demo at the end. So the intention, I've alluded to this a couple of times before, not just phase distortion and virtual analog, but actually a complete sampling synth as well is going into PIANA. Now, at the point I presented this deck to Bristol a week ago today, sample playback was kind of a coding in progress and wasn't quite there yet. And since then, I've got some pretty epic sample playback in place. I've got an entire mellotron and some awesome voices that I've got from Jordan Rudess, actually, who is one of the synth gods, and I'm doing some work with him for an iPad application. So I've got some of Jordan's custom stage sounds, which sound awesome coming out of the Raspberry Pi. So yes, 2 sample-based synths are going into this baby. One of them I've called Pianatron because it's piano, but it's a mellotron all at once. Awesome. Looking at typically minor third interval sampling, so you've got 3 keys per sample, so you get a bit of chipmunking, but heck, the Raspberry Pi is an inexpensive piece of kit. You can't really expect you know, layered velocities and all that stuff. Looping and envelope generators. So the cool thing about the sampling synth that I've put together is I've retained as much of the modulation matrix as I could from the virtual analog synth. So the envelope generators are carried through. Frequency modulation rather than phase modulation is also carried through. So you can modulate the pitch with an LFO. You can modulate the levels of the 2 oscillators. So think about it as oscillators, right? Whenever you hit a note on the sample playback engine, 2 samples are being triggered at the same time, and they're conceptually oscillator A and oscillator B from the virtual analog synth. The modulation matrix has got this great feature whereby you can apply an envelope generator independently to one of the oscillators compared to the other, which gives you the opportunity to ramp up oscillator B more slowly than oscillator A. So for example, if you build a voice which has a pretty dark, deep sound for oscillator A, and then ramp up oscillator B and it has a much brighter sound, you get this blah thing going on, which is, you know, although rather more tuneful than that, which sounds absolutely brilliant, and I'll show you some of that in a little while. So that's Pianatron, the Tron on piano. The other one, as you would expect, is a drum machine. So percussion, piano and percussion, sample-based drum machine. I've got a complete set of Lindrum LM1 sample, actually LM2 samples as well, and some old analog sounds as well, which have been sampled. So the drumming is going to sound great on this thing. It's very much going to be about synth pop, though. It's not about attempting to be Keith Moon. It's about attempting to be the backing track for an old Vince Clarke record. So there you go, 2 sample-based playback engines. Now, here's the interesting one. If you were to use all of the features that PIANA now offers, if you were to go back in time and buy the pioneering synths that did these things, how much would you have to spend? And it looks like around, I don't know, well over 20,000 quid to buy what a $30 Raspberry Pi can do in 2012, which is pretty awesome, to be honest. And it's not the fastest machine on the block, so the fact that it can do all this at all is amazing. The fact that it can do 20,000 quid's worth of synthesizer for $30 is staggering. Here's the question. So, let me wear a member of the audience hat. How much is this thing and where can I buy one? And the answer is, I just do not know yet. I may put once Kickstarter are up in the UK, I may put a Kickstarter project together to fund the development of this, because it does need a real MIDI interface. Now, I could use USB MIDI for this thing. I've been honestly having a bit of jip with USB MIDI on Raspberry Pi. It's not working as well as it could for me. And it crashes the performance of the synthesizer horribly. It seems to just burn a lot of CPU trying to do USB MIDI. Could be me being a bozo. But the other more important point about using real old-fashioned optocoupler MIDI is it means you can use a really inexpensive synth. So right now you have to use a class-compliant USB synth, which means you need something like an Axiom. If you're going to buy an M Audio keyboard, right, you need an Axiom rather than an Oxygen. Which puts you a couple of £100 more expensive for the keyboard. So by using real MIDI, you can actually use a non-class compliant MIDI output keyboard and save a couple of £100 on your overall setup. So in terms of how much and when, can't answer when yet. It shouldn't be expensive. I do want to build it as a piece of hardware, and if I can find some way to protect my intellectual property, I wouldn't mind bringing this out just as a piece of code. So we're looking into that right now. So there you go. That is, thank you, that's PIANA. Let me turn my machinery on and I'll give you a swift demo of both the phase distortion and the sample playback. And yes, thank you.